All right, so yeah, finally, welcome. It's short after 1 in England now, so we are right in time. Good, so we'll have the challenge pitches now. Let's just switch to the next slide. Okay, so here are the challenge pitches. So this is the presenter. I will connect it to Erkin's laptop, and if you want to click forward, you can do it with this thing. So here's a huge button for forward, and there is a smaller one for backward. It does not have a laser pointer, so you can only click. Okay, the order of the challenges you know already, so we'll just stay in the order, and our host for the challenges is Lars, and I immediately hand over to you.
Yes, welcome from my side, one last time at least. We are very much looking forward to all of your challenges, and last night we told you what's relevant, and now we will see what came out of these 2 days that you had to work on these really cool projects that there were. So we'll just stick with the order. So if you are C1, you will be the first ones, and if you are C5, you will be the fourth ones, because C3 does not exist or did not happen. All right, so, and without further ado, I would just ask Julius Bünger and Ahmed Amin Shafiq onto the stage to present their project, which was hardware, software related reverse engineering. And let's see what they did.
Start the counter for yourself. Very good.
It's another minute.
Yeah, yeah, exactly. So it runs as slow.
I just start when the clock starts. Okay. So hello everyone. Hello everyone. Today I'm going to present, along with my colleague Julius, what we have done in the project hardware-software mashup with reverse engineering. So, actually the pointer doesn't work.
Yes, just click it.
Okay. So actually, we were trying. The main idea of our project is to try to get into hardware and know what is the logic behind its functioning, namely communication, software, and the other behaviors. So we were handed like 2 different type of device. A first one, which is a home hub. So the home hub is used to interface with all devices that use IR technology. So the idea here is to have to use your smartphone, your laptop, to power up your old TV and your old stereo, etc. that works on IR. The second one. So we didn't have the picture of it. It's a Bluetooth device that actually have a microphone and reacts to the movement, to the sounds made by the external noise, and can be also controlled through a smartphone. So as we say, the idea here is to know more about the protocol communication of these 2 kind of device, namely Wi-Fi, Bluetooth, and RF, and to figure out to gain access to this device to explore the full, to get the full advantage of the device itself.
So, do you hear me? Okay, that sounds better. So the underlying challenges were to interface with the devices, because that uses an IR control. We had the remote control, and we could pick up the signals. Sorry. Yeah.
Take your time.
Yeah, that time. I'm taking it already.
Okay. So obviously Julius was more into the tech itself, so which allowed me to explore more about the presentation, about what I'm going to do. So basically, like if you compare the evolution of device, you will see that this device still deliver the same option. Like the TV still render images and everything. The problem is that lately now we have too many e-ways with the device that deliver the same quality of service. So in order to recycle things, we can just use the hub. And the problem is the current hub does not have the advanced option to set up scenarios, scripts, like what makers do. So they just have like a UI that resembles the remote control. So the main idea here is to recycle devices that offer the same quality of service and adapt them to the current technology that we have. And also like the problem, like the challenge here is, as we said, is to gain access to their technology and to see what we are going to do with this thing.
Yeah. Okay. So what methods we were using is we were looking into flashing different firmwares or trying to. We had this infrared controller which could pick up the signals of the remote control, so we were looking at that. But we had to use it in that way, so we had to flash a new firmware. First, we tried to flash it via Wi-Fi, which we managed to break the device with. So we had to go down to the soldering level with the hardware. This is the thing right at the bottom, so we flashed it successfully a second time, this time now into an operable state. That was nice. We analyzed the infrared communication. We had also a look at the second device, this sound bar flashing LEDs. And we tried to identify how the communication worked there. We checked it with the Android device, which was nice, but it was a bit too complicated for now. So we present mostly the results with the IR. We had a lot of trials and some errors, some success. And yes, also, of course, we needed to identify for the different hardwares, we needed to identify what hardware is there, what chips are there, to know how they function. Also, me? Okay, so we tried to split up the work. It's hard to define how, in terms how we defined it, but you can roughly say we did it more in a hardware-software level, and there were different tasks involved. As it was reverse engineering, it wasn't straightforward to put milestones there to see from the beginning what would be the challenges. But you can roughly say that it was first about understanding the device, the communication. Most importantly, I think most of the work went into setting up the toolchain. So getting this IR device to do what it was supposed to do. And on the other hand, with the Bluetooth thing, try to interact with, to get a connection to the device itself. So we tried different libraries for interacting, for controlling Bluetooth devices. All of them succeeded to some extent. I wouldn't say I'm able to control Bluetooth devices programmatically now. So, but I learned something in that direction. So maybe the time was just not enough. And yeah, of course, we had a lot of testing and validation, which the ones who were already there just before the talk, I think you noticed some of that. So yes.
So as you can see, sadly, due to time limits, we were more into getting the device to be hacked, and so we didn't have time to take more pictures. But as you can see in the first picture, it's the tear down of the controlling board of the hub of the IR hub, and like surprisingly it was running on a Wi-Fi chip. It's an ESP82666, which we know how to deal with. So we try to look into the documentation to see how we can get into the device. We succeeded to do it first wirelessly. It was a problem with the version of the software. Then, as you can see, we soldered cables to gain access to force like flashing through serial connection. And finally, we succeed to do it. So in the second picture, you see the sound bar along with the timer and the Raspberry Pi, and I will show you why we used the Raspberry Pi. So actually, like the device works on its own. We have like the timer who is controlled through IR remotes. We have the chip who is trying to convert like comments that are received from the Raspberry Pi and then transform them to IR codes. And the Raspberry Pi can be accessed through SSH. So the main idea, which we didn't have time to, is to develop a UI in the Raspberry Pi. So it will be a standalone object that we can set timer, we can set countdown, we can change time, etc. And then, as you can see, we hopefully succeed to flash it using a browser flasher. There is another slide. Okay.
Okay. We are running out of time, kind of. So, what the achieved results were, I think we already covered a bit of that. So we managed to have this device which now controls the time, and we basically copied all of the functionalities of the infrared remote control and have it now available as a library kind of thing. So currently it's a simple Python file which does what it's supposed to do.
Okay, so the purpose of the of what we have done is to generally target the maker community. So we provide, we have developed a CodeMD file, which have like first early version of all the steps that should be done to have the same access that to walk the community through what we have done, and it's precisely for presentation, as you can see now, as we have exceeded our time limit. So I hope that you enjoyed our presentation, and we are really happy to show you a demonstration. And then if you have some questions, we're really happy to answer.
Awesome.
I actually think we're still in time.
Awesome presentation. So great work there. I have a question to you. So what do you think was, well, the major difficulty throughout the last 2 days? So which task stopped you the most?
If you have a good answer, I'm thinking about it.
I think mostly the hardware. So like the clock sometimes behave strangely. So it's a cheap clock. So it's sometimes the sensor does not synchronize with what we are sending. So it sometimes bugs, but like 90% it works. And also the thing is it's like quite challenging to flash it wirelessly. And yeah, I think that's it.
I think I want to add to that now that we have this time limitation in double sense. Like, we could have probably achieved more with more time.
Okay, yeah, thank you very much. So give it up one more time for this challenge number 1. While we're doing it, I would like to ask the next team to come up. It's going to be C2, Chicken. And while
They want to make a demo.
Oh, sorry. Before that, apparently we have a demo.
Okay.
Sorry.
I tried to. And now I do. I will see it first and then present, so you don't need to look at there. Are you sharing your screen? I think so, yeah. Okay, this is what I see. I can stop it again.
In the meanwhile, I would like to thank our jury that is also here, grading all of your presentations and submissions. So we have very high caliber people here. We have
Okay.
Nicolas. And we have Laurent and Fabian as well in the front here. And you are not grading Marc-Oliver Pahl. Yeah, and Marvin, sorry, yeah, Marvin as well. So they're all here listening to your presentations, and I guess we are now ready to see the clock in act.
Yes. So as you can see now, like we are going to turn the clock off.
Yeah, I try to. This is one of the problems we discovered. We don't know how to turn off the alarm yet because the clock is. So now we turned it off because I was able to because the alarm was off. Please go on. You were wanting to say something and.
No, it's okay.
Okay, so I turned it off. I tried to turn it on. It's also the infrared that is sometimes not that reliable, so it worked now. We have all of the functionalities of the, why the alarm? We have all of the functionalities that are on the remote control, as you see with the autocomplete. And we have also the opportunity to do something like automation. Like for the set time, you need to use different buttons in succession. So set timer does exactly what you saw before. So it's sending one key, sending another key, and so on. So in the end, the timer is set. So this is great because you don't have to press the remote control every key, and you can also automate like whatever you want. You can change the time, you can change whatever. So this is great, I think.
Awesome. I'm sure we're gonna use it. I'm very sure we're gonna use that at least in the next PhD school. All right, so now we are done with the first challenge. Thank you very much. Good job. And we will continue with chicken. So C2, about building automation. So BACnet over BACnet using LoRaWAN. And yes, please come to the stage and I'll hand over a microphone.
Yeah, thank you. We are the chicken, at least the ones that's still here. So yeah, I'm gonna try to go through this. We have something to change the slides. So what we want to do is to use the new technology LoRaWAN to transport information. And what's very good with LoRaWAN is that it's very energy efficient, so you can run it for a long time with little energy consumption on small devices, and for much longer distances than a lot of other protocols. And what we want to use this for is to transport a protocol called BACnet, which is used to monitor buildings, larger buildings, temperature, humidity, etc., which makes it very suitable to use on LoRaWAN. The problem with LoRaWAN is that you can't send very much bandwidth, so we need to compress this in some way, and this is where Chicken comes in. So Chicken uses static values on headers and uses rules instead. So instead of sending always 3 bytes with the same value, we identify that this is a specific rule, and we can just send 1 bit to identify that specific rule, and in that way send a lot of less information without losing any data. What we have seen as a challenge here is that BACnet is a proprietary protocol, so we need to use a simulator to reverse engineer the protocol, and we have needed to understand both the BACnet protocol and the IPv4 protocol to be able to achieve this. So, as I said, BACnet is proprietary, and we didn't really understand how to communicate with the simulator at first. That was challenges we had to find out. And the end goal here is to be able to parse both an IPv4 layer and a BACnet layer, and using Chicken to compress this to be able to send it on LoRaWAN in an effective way. So just a small list of things that was supposed to be on this slide, but we didn't have time to do that. So in general, what we wanted to do was to be able to parse IPv4. There was only support for IPv6. We needed to understand and parse the BACnet protocol, and then we wanted to be able to create rules for BACnet and IPv4 to be able to compress it, and in the later stage send it to over a LoRaWAN, and in some way create a big success.
Okay, so basically, what were the achieved results? First of all, we used the BACnet simulator to get all the packets from the BACnet simulator. So we need to extract the traces, save them in a pickup file with Wireshark, and then we need to reverse engineer the BACnet protocol to see what happens with that. And so we built like this setup with between 2 laptops. In one laptop we run the simulator, in the other we connect the one that get the traces, and with Wireshark we are able to get all the packets from this simulator. So we did these setups. It was really challenging for us because the simulator doesn't have much information about it. So to connect between 2 computers in the same net, it was a bit challenging to take us like half a day to do it, but we were able to do it. And once that we were able to do it, we have with Wireshark these packets. So in this way we can save this data, save in a pickup file, then and we need to look for all of the headers for BACnet and IPv4, and then do it with the process of compression with Chicken. And then we need to read this pickup file. So we need first to see all the layers. So we have Ethernet, IPv4 in the first image, and then we see all the headers for IPv4 that we have the version, the identification, some time to live, some these kind of headers for IPv4, and then for the BACnet protocol, so we have some types or the length, the version, the control, and we have different layers for BACnet too. We have the built-in automation control network, APDU. So we need to do this stuff. And finally is that we have some code in Python that we, with Scapy, is a library that allows to read the pickup file with the Wireshark trace packets. So finally, what we did was to reverse. For IPv4 was really easy, but it was long, take a long time to review all the headers. And then we need to put all the headers inside the chick file, and because nowadays chick is only available for IPv6, so in this case other rules are built for IPv6. In this case we are able to build one rule for IPv4. The next step, after review all the IPv4 headers, put it in the parser, we need to, we create the rule for IPv4 obviously, and then we have some, when we are building the rule for the compression, we said we are not going to send this, we are going to compute this, or we are going to ignore that. And in our case, to build the IPv4 rule with UDP, we were not able, we don't have too much time to build all the code for all the rules, so we only did it for IPv4. For BACnet, we are able to do it and just to build the headers and get it in the code, but not to build all the rules for the compression. So if we see, I want to come back. If we see right here, we only have the IPv4, but when we do the compression, we get some results. Obviously, for some packets we have like 51%, for some others 30% of compression. So this was really good to send through LoRa. And then if we could have better results if we go further with the BACnet headers, right? So as I told you, for the BACnet headers, we were able to get them, some of them, with the packet from the pickup file, but we will have time to do it, to build all the rule for the chick library. So basically the impact and the outlook is that we can have BACnet that is over IPv4 right now, sending to LoRa network and use this. So yeah, basically is that. Thank you.
Great presentation. In particular, you stayed within the time limit. Very well done. Thank you, Marcus and Sebastian, for this great presentation. I guess are there any questions from the audience? I guess doesn't look like it. Then I have a question. How difficult or how suitable do you think it is so now this one part was replaced with a simulator? How easy is it to connect your stuff now to like a real system?
Nowadays, I think if we can take the data from the internet, is with just some file that it would be reading the data from the device, it will be really easy to connect from the code because it's just passed through the data. So with the pickup files, we are just simulating the real environment. The simulator just takes some data through the internet. So actually, the next step also is maybe not reading through a file, is just take the real data, go through.
All right, yeah, thank you, very interesting. Then one more time, thank you to the challenge presenters. I would like to ask the next challenge that will be a little special presentation because one of the students, so Leila and Alice, worked together, but Leila was actually working remote, so she's one of the remote participants. In the meanwhile, I will ask the jury to just conclude their grading of the previous challenge. And Then Erkin will share the sound, so Leila will actually join us via Zoom for the presentation. We will have her sound on stage. And then Alice, I would like you to ask to come on stage for your presentation.
I think yes, but she's not connected. So she sent me an email to say that she can't connect, but I sent her my phone number to speak with her to explain.
So you have her on the phone?
Sorry?
You have her on the phone?
Not yet.
Okay, but because if you say you need some more minutes, we can also just exchange the audio.
Yeah, I think it's better. And next,
Okay, then we have a short shift in schedule. We will switch the.
And for the jury, that just means that you can click next probably, and then afterwards back, and then you get back to the form for this.
Unfortunately, you cannot, as all the inputs are required. So I guess,
okay.
so we will just keep.
But then let's just continue, and we just note down that there where it's written C4, it's now C5.
Take a note. Yeah. So the next ones are Alexis Duhamel, Dairo, and Deruk, and Victor Goman for the open source vehicle. A more security related challenge, and let's see what they found out for their challenge. So the next 5 minutes are, no, not even 5, 9 minutes.
It's a PowerPoint presentation, isn't a PDF, right? It's PowerPoint. Yeah, it's good, yeah.
So the next 9 minutes are yours, so please take it away.
Hello, I'm Victor, this is Daigo, and that's Alexis, and we are going to present our open source vehicle hacking. So, next. All right. So we're going to start with the context and the state of the art. So for context, we are working with the open source vehicle that is developed here. Since it's open source, it means it will get attacked more easily. Attackers can know everything about their target, so this means that the system must be secure by design, so it's more dangerous than a closed source system. We are going to attack via the infotainment system, and this is already done. This is needed for autonomous cars, and it is an attack pretty known. For example, the T-bone attack attacked also via the infotainment system on Tesla cars. Normally, the cars aren't connected to the outside world, so that makes them safe since they're isolated, but with IoT, they are connected to the outside world, which makes it possible to attack. So we are going to start with the underlying challenges and the key objectives. So we are going to start with explaining the architecture of the network that we had to hack. So we had only one access point, that's over here. It's the infotainment Raspberry Pi. It is connected over the Wi-Fi, so this was where we could get in. The Raspberry Pi was connected via a serial cable, via a serial connection with the screen interface. But as you see, the screen interface is red, and so is the LiDAR. This means that this is not fully developed and working, so we had some problems here, so we could not get on the CAN2 network. On the CAN2 network, there is the key and the smart controller that are speaking. CAN is a communication protocol for serial languages, by the way. And over here we have the CAN1 network. This is a critical infrastructure, and this is where we want to get in. Over here you have the back interface, the driving interface, the motor interface, and a front interface. And it is basically how the car works. It is the speed is stored here, the angle of the steering wheel, the brakes, lights, everything is stored here. And there is also a Bluetooth connection, but that's also not really accessible. But so because the project was not 100% finished, we could not do the full attack. But there is a theoretical attack possible. This would start by getting into the Raspberry Pi and then via a serial connection taking over the Arduino and sending commands from the Arduino to the CAN2 interface to the central controller and then finally to the targets and change the values. Since this was not fully possible, since the Arduino wasn't properly working, we had to do a physical attack, and we connected our Raspberry Pi once we were in to the CAN1 interface to see what we would be able to do and how we could damage the system. So I think now Daigo is going to take over.
All right, so I'm going to talk a little bit more about what methodologies we used to get in and how we actually performed the attack. So for methodologies, we first looked at the OWASP top 10 itself, so like default credentials or weak and hard and guessable passwords. Then if that wouldn't work, we would use brute forcing and fuzzing to get in. Also, if you were in, fuzzing itself would be very viable because you could overload the network itself. Because the key fob itself is RFID. RFID, you can clone. This RFID tag you could clone as well. It's the same frequency as a normal NFC tag. And sniffing would also be viable, but because this is a total open source vehicle, you wouldn't really have the need to sniff anything because everything is already accessible. For the attack itself, we exploited CAN1, or we could exploit CAN1. And if we succeeded, we could do anything from changing the steering wheel, the target values, the brakes itself, so tricking the vehicle into thinking that it's driving in the wrong direction or that its brakes are active or whatever. A denial of service attack on a vehicle on a critical network itself is pretty dangerous also. A denial of service would mean that the system itself wouldn't be able to communicate anymore. So the brakes wouldn't be able to communicate with the central system or the lights or whatever, causing a crash most likely. On the CAN2 network, we had a theoretical attack because the CAN2 network was also had also some interesting functions like the breathalyzer and LiDAR. With an exploit on the CAN2 network, we would be able to fake the driver being drunk and causing the car to totally stop and stop functioning. I'm now going to show you two videos. The first one is our advanced hacking technique to get in on the top. Here you see it. And that was it. It was advanced hacking. So getting in was just over SSH, and default credentials were still there. So it's the first thing we tried, and we got in. That's why a Raspberry Pi is pretty much overkill for a car like this. And the second video on the bottom is the fuzzing that we did on the light system. Yeah, so that really breaks everything. And if you leave the fuzzing on, it causes a total overflow attack and denial of service as a result. All right, now we will discuss the mitigations of our attack. Here you go.
Thank you. So speaking of mitigations and how to defend the system against such attacks, we tried to think about how we could prevent the ways we were accessing the device. So the first way we could mitigate such attacks is to make the RFID key more secure. More specifically, try to encrypt the key stored within the RFID device, and also maybe try to make it 2FA, two-factor authentication, so that we couldn't do anything really with a flashed NFC tag. Second mitigation technique would be to make an actual heartbeat on the CAN network. So since you cannot see if there is an additional node, a malicious node, trying to communicate with your own nodes on the CAN network, you can try to have a system that sends a heartbeat message to make sure that the system isn't compromised. So this goes with a frequency-based messaging system, which has been shown in the reference we show on the bottom. Basically, the system is that you can, since you can see when you are receiving messages, you can study the frequency of the messages. If you are receiving messages too frequently, that means that someone or something else is speaking on the network, which most often means that you have an additional node which potentially could be malicious. Eventually, we try to think about a system to recognize if you have a physical node on the network. Unfortunately, that kind of mitigation defense couldn't work on high-speed CAN network. However, it could work on slow-speed CAN network. So in terms of impact and outlook, well, basically, such system consisting of only a CAN network is already hard to attack because everything is kind of isolated from any remote access. Still, if you try to make it more complex, like having autonomous capabilities on your car, you have to make the system more complex and maybe introduce more vulnerabilities. So that would be something to care about. Also, well, as we mentioned about the RFID keys, it may need to be more secure because currently we couldn't flash the RFID key with our NFC chip on our phones. But if we bought some kind of NFC tag, like maybe 15 to 20 euros, we could potentially copy the key and have access to the car. And lastly, well, as Victor mentioned, Raspberry Pis are a bit too powerful for what the OSV is trying to achieve. So maybe try to find a more suitable target for performing the computation. So that's it for our project. If you have any question or remark regarding how you would have accessed the car and device, would be appreciated. Thank you.
Awesome presentation. Thank you very much. Are there any questions in the audience? As always, I have a question for you guys.
Sure.
And this is, so what are your takeaways from doing this? So are there 2 recommendations you would have to the OSV for preventing such things from happening in the future?
Well, firstly, I believe having any kind of remote access to the car itself introduces vulnerabilities, which is why we were stuck at the door in the first place with the non-working screen interface. Well, still, you said about Bluetooth maybe?
What?
The Bluetooth device and...
Well, mainly the Raspberries are too powerful and can actually be used against your own device because there were even some hacking tools. The tools that we used for hacking were already downloaded on the Raspberry, so we didn't even need to do that much. So I'm not a huge fan of the Raspberries. Also, the SSH port was open, which is basically just giving an entry point and letting them start, which shouldn't be able to happen. And also the RFID should have can be better encrypted, but of course it's a prototype. But a better RFID, as said, is needed.
Yeah, and also just a tamper-proof CAN network that if someone is tampering with the network itself, that it could be just stopped completely is also pretty handy.
Okay.
However, overall the system is actually pretty secure with the isolated CAN network. That already makes it quite hard to have any kind of access. Still, the physical attack we've done wouldn't be quite possible because accessing the CAN network itself is like very hard in the car. But if you had access, since you already know the messages that transit through the network, that would make it quite dangerous actually.
Okay, yeah. So drunk driving via machine learning. Okay, thank you very much for this great presentation. The jury is already done, I guess, with their stuff, and I would ask does the remote challenge setup now work? It does not. Okay, then we will continue with challenge number 6, which was the live processing of real-time data and also analytics. And we have Eva, Baptiste, Sylvain, and Abdelhamid, who will present this challenge. Here we have them, and the next 9 minutes are yours.
Thanks. Our project was to do live data analysis on processing. So the idea was during the live stream that is happening right now, to when some keyword are pronounced, to send post on social media with a link to this live stream, and with the keyword on a little sentence to make people want to come to the live stream and join. So our project was like a mix of different things. There are some part of IoT because everything like it's a network, like we have the microphone connected to a computer that stream everything with the cameras, and on another computer has to listen to the live stream to extract the audio and do all the computation and send them to send a post on a social network. We have a lot of data because there is hours of live stream. We have like machine learning to recognize the word and find the one that we want to use. And we have like data analysis also. So what are the clear goal of this project? The goal is to create engagement by processing in real time keynote live stream to make content for social media. There are some kind of similar things with virtual smart assistant, like OK Google, say Siri or Cortana, where when they listen to some keyword, they will do some action. Some of the drawbacks of own methods was that like the context could be more noisy. Like for example, before when last introduced some people were uploading, so like it can create artifacts or noise that make it more hard to listen. We want more keyword, not just like OK Google, but like a lot of keyword like security, IoT, hardware, software. There will be more than one speaker, and every speaker can have an accent, so like it can be harder to find like to fine tune it to be the best way to detect the word. And it's an indirect approach, like contrary to like the smart assistants. It don't listen to people directly, but it listens to a live stream in which people are talking to an audience through a microphone. And why would you want to use this tool? Because like it could attract new viewer. Now because of COVID, it could be a great way to make people come to a live stream, to listen online, to interact at the end, to ask questions. So in this era, it can be really relevant.
Okay, thank you. No, we have we can split this project to 3 steps. The first challenges is to the data extraction. The second one is the machine learning and the data processing. And the third is the picture editing and social media posting. As we can see here in the pipeline, we have the data extraction, which done by me. We have the live stream. We first cut the video every 13 seconds. Then the extract audio and the screenshot using YouTube DL tool and FFmpeg. Then we pass it to the machine learning step, where we use two solutions. The first one with the iOS toolkit, and the second one with NLTK and the Wave2Vec model, the pre-model with the Facebook pre-trained model. Here we do the speech recognition and the keyword extraction and identification, using this keyword and the picture as the input to publishing in social media and posting like Twitter using the Twitter API.
Okay, thank you. In this slide, I will talk about the detail of our implementation. The last slide presents the methodological pipeline of our work. And so we have based our implementation on 3 steps. The first steps consist to use the library, the framework, and Neltica. And the second step consists of using Amazon Transcribe and Amazon Comprehend to process the audio file. And the last step consists of using IBM Watson library to evaluate. Our objective or manager was to compare, to have just a small comparison, but using different method. So here in this slide, in this two figure, we have in axis the keyword from a live stream that we have extract audio and process by machine learning. So in the first, I think in the first we have the result obtained using the Neltica library and the Facebook pre-trained model. And the second one is the AWS Amazon Comprehend service. The real difficulty that we have you have seen when evaluating the two methods that using the fine-tuned Facebook model, we see that we extract the keyword like AWS Amazon Comprehend, but the context of the live stream is not taken in account. Why take in account? Because we have to fine-tune this model to have good result depending on the topics that we are working with. And using AWS Amazon service, we can see that the length of the word are very big, so that Amazon model take in account the text and comprehend the text and take in account syntaxes and they fill and if this has a scientific is in IoT or another subjects, it take in account the subjects that contain in audio file. After this, we can show that in our process we are able to process all the audio file and the video and post it in a Twitter. We have, for example, an account Twitter that we have created, and then process our video and send it to Twitter. For image, so we are able to send just a link. Because to send a video or to send an image in Twitter, we have to Twitter impose that we have an elevated account, so that we can process them to evaluate or to do something using Twitter API to process it. We have to create an account or to give more information about something that we want to process is imposed by Twitter. Okay, in this last slide, just want to give some key that we can improve our work. Firstly, to process an video file in real time is very difficult because we don't have the total duration of the work that the signal that we are processing. So many methods are proposed, but it's still difficult because we can have some overlap when processing, or the audio file or the video that we are extracting time by time can be split and then it's possible that we have a high probability to the system cannot comprehend the context and the subject that we are talking in the video. That is the real difficulty. And another difficulty, another way to improve the work consists to fine-tune the YouTube model that and the YouTube Facebook pre-trained model that we have used. Thank you for your attention.
All right. Thank you very much. And if I have understood it correctly, this thing is already working, and you can just put it to any YouTube live stream.
Actually, we have a problem with the FFmpeg. It's like what we explain here in this part. We use the FFmpeg tool. That tool is open source tool, but it works only for some version, some distribution of Linux. It's not work for all. This is the first problem. And the other problem here, to publish any picture, we need a professional Twitter API. This is the problem. Well, now we can only publish a URL and keywords.
Okay, yeah. Very interesting work you did. Are there any questions from the audience? I guess not. Then thank you very much one more time to Amit. Okay, then we have the next. You probably need the cable. Where is it? Here we go. Cycle. So the battery powered scooter or electrical bike, and yeah, so I will hand you over the microphone. Do you want to stand over there?
Yeah, I think it's
okay. Then the next 9 minutes are yours.
Yeah, so thank you. So I'm Alice, and I work with Leila, but Leila couldn't be here today, and she is not here online. So I have a little record. So I think it's work. I hope. No. Ah, yeah. Oui. Ok. Okay. I'm not sure about sound, so. No, the sound is here.
I'll put the microphone there, maybe this helps.
I just test.
Rinse.
Yeah, okay. So.
Once upon a time, in the not so dark Ren City, a tricycle dreamt of being a Batmobile. So it went to Marvin's garage, the place where all the objects with identity crisis go to get geared up. After a long procedure, Marvin successfully transplanted a Batmobile chassis, an engine with significant amount of horsepower, and a decapotable ceiling. Also Batwing doors. But the procedure didn't go exactly as planned. Although the Batcycle now looks like a Batmobile, it is basically blind. It has no eyes. Sure, it can still park in a disabled parking space, but it has to get there first. And that is our mission, should we choose to accept it. Spoiler alert, we did accept it. Our mission is to provide it with bat vision. Now that technically translates into providing it with a system that picks up danger related to front and back collision. The system will have to detect objects in the front and the back, pick up the current speed, compute the level of danger according to which it will display a warning. To design and implement the system, we relied on the programming and simulation platform gracefully provided to us by Vita Science, check them out, and we wrote our code in Scratch and tested it with Arduino simulator. For the sensors, we used a light detection sensor, a LiDAR, and a tachometer, which measures the rotation speed of an object. And, well, now I will give the floor to Alice. She will demonstrate to you the groundbreaking result we have achieved. On n'est pas à l'abri d'un Nobel.
So, now to achieve this challenge, this challenge is here, and so to achieve this, we decided to use LiDAR. So the LiDAR work as eyes for back cycle. So this sensor give us the possibility to evaluate the distance between the bicycle and another vehicle, or for example a person. So this is we have this sensor for distance, and we have another sensor that it's called tachometer or odometer. So this sensor count the number of wheel spin, and with this information we can compute the speed of the bicycle. So with the distance and the speed, we can have some information about the bicycle, and with a little compute so it's a little compute and easy way to create a code with block that we use Vita Science to compute our code, and so we compute different degree of danger. So for example, we decided that for 1 meter or 2 meters, for example, if we have just 2 meters between the bicycle and another vehicle, it's very dangerous. So we can display on a little screen an information for the user that it's very dangerous and you have to be careful. So this is the achieved results. I hope it's work. Okay. So I just show you the video and then I explain. C'est bon. Okay. So on this video, you can see at the first time the little leader in front of the bicycle, and next you can see the bicycle, and at the end you can see so a boxes when we put our material. And so you can see the screen, and you can see the Arduino shield that Leila spoke before. And we have put a leader in the back, or because we can have information about in front and in back, and the information for the back is very important for the user, because the user don't see the vehicle behind him. So when everything is good, and when the user is in a good position and no danger, the little screen display the speed and the distance in meter. Oh no, in centimeter, for example, sorry. And we have a little smile to say that it's good, nothing could be happen. And so the second video. So when someone pass in front of the bicycle. Oh là là, mais c'est fou. So the screen change, and we have this information. Be careful in front, and a little icon to represent death and danger. So to conclude with impact and outlook, so the bicycle is now relatively safe to use and ready to be part of IoT. In fact, to imagine some connected vehicle for IoT, for example, we have to we need information to exchange, and so in this bicycle, at the beginning we have no information to exchange, and now we have information about distance and speed. So the next step is imagine 360-degree detection of object. So we can just add 2 LiDAR to detect other objects in right or left. And we can imagine too 5G connectivity to run nearby connected vehicle, and inform that, for example, the vehicle in the back are too close to the bicycle. So thank you for your attention, and if you have a question, okay.
Awesome talk. Very interesting touch. In particular, good job with the remote experience. So, are there any questions from the audience? None. One from my side. Was there anything that surprised you in the process, or was it extremely difficult or easy to implement this challenge?
So for my part, I think the most difficult is not that Leila is online, because we have a good feeling, and we are okay from everything, so it's very good. But I think the most difficult is to choose what we do, because we have a lot of possibilities, and it's very difficult to choose
So okay, we just stop and go implemented, and it's because we have a lot of possibilities, a lot of sensors. So yeah.
Okay, but very well done. So one more time, one applause for Elise and Leila, remote. And this concludes our presentations. So the jury will now have a few minutes. I guess they will meet upstairs and discuss what they have decided. And they will be back in roughly, probably 10 to 15 minutes. And then we will know who the winner is of the challenges. So yeah, see you.
Yeah, so big thanks also to Lars.